Um, all right, so we're very happy to have for our next speaker, Robert Owczarek, and he'll be talking about Cartan philosophy on geometry and TQFTs defined for theories of Sławianowski and Kijowski type. Sorry.
Kijowski.
Yes.
Kijowski, yes. A lot of Polish names.
Yes. Yes.
Sorry for that, but just happened. So I should first say that I am very honored to be a speaker at this great event, and I am humbled because so many great knot theorists are present, and I am just a simple mathematical physicist who sometimes does a little of this mathematics, which I hope will be interesting. And I wanted, of course, to say the happy birthday to our Lou Kaufman, and both I and Hannah, who will speak next on this on related subject, say, 100 years from now, in good health and productive years ahead. And we are very sorry that we've lost Roger Fenn, who was also on the committee, so we sadly remind his, yeah. So I wanted first to say also a few words about my relationship with Maya and Hannah's, because we are like everywhere present in pair. So that we know Lou like for 25 years, estimately, and Mexican connection was important on that because of our common friend Zbyszek Oziewicz, who unfortunately passed away. And I was looking for the oldest pictures from such events, but the oldest I found was from 2002, from our Acapulco interesting conference. I mean, it began in Cuautitlán, but then we moved in very strange ways to Acapulco with many stops on the way. And it actually was great because we've spent a few hours in a bus stop, and Lou was teaching us about knot theory because he always has with him some piece of paper to write formulas and a couple of pieces of strings to show what he has in mind, etc. So it was great. And of course, many times from then, long list of visits. And here is already in Acapulco. It was in a room which was shared with Disco Boom Boom. I mean, they were doing this at night. We were having our conference during the day. And the atmosphere was so relaxed, but still very productive that, for example, Professor Przytycki was so eager to use the opportunity to play tennis and unfortunately hurt his nose. So I am sitting here between him and Zbyszek Oziewicz and Lou Kaufman, probably thinking, should I rather listen to these great guys or comfort our friend? Because, yeah. So now back to math. So what interested us, I mean, Hannah and I, was to define along the way, similar to what was presented by Professor Wheaton yesterday, quantum field theory, or rather we start from classical field theory and then quantize it in similar vein as Professor Wheaton long ago did, but presented again yesterday, but do it also for other manifolds. And our inspiration was actually Einstein's general relativity, because this was like first geometric theory in physics, and because the Chern-Simons is like for already other theories built over manifolds like electromagnetism and Young-Mills, etc. So I start from Einstein's general relativity because of that and how Cartan criticized it. Then I will talk about topological quantum field theories with and without metric, and focus then on those without metric and try to marry this approach with Cartan's approach to geometry, more or less. So since we are inspired by Chern-Simons, I will briefly remind this topological quantum field theory, which is like the root of different approaches to topological quantum field theories, but this one is without metric. And of course, I think holonomies resulted to this Chern-Simons, and in case of flat space, did the job for knot invariants, in particular John's invariant was described this way. So now, after this introduction, I will try to present how this Cartan's philosophy combines with philosophy of topological quantum field theories, and show that this relates nicely with theories which were long ago formulated by Sławianowski and Kijowski, who were not at all thinking about topological invariants, but rather thinking about some different approaches to general relativity or similar theories. And the technical piece there is that Lagrangians, and in this case, Lagrangians means functionals of fields, which contribute to the action of the field theory, not as often is in the jargon of knot theories. Lagrangians are often Lagrangian manifolds, Lagrangian surfaces. This is different thing. So we build Lagrangians with scalar densities, and I will mention how it works for Kijowski, in particular as a metric-free theory. And then I will talk about something, I mean, a bit different than Sławianowski really created, but an affine for reformulation of Sławianowski theory, because this will fit nicely with this Cartan's general picture of geometry. And Hanna will actually talk about Sławianowski theory in its original formulation in terms of frames and coframes. And I will end more or less with just formulation of the topological invariants for manifolds of those topological quantum field theories based on the fundament of those two theories. And of course, I will end with some discussion of that. So let's remind Einstein's general relativity. So standard Einstein general relativity uses metric as a basic field. And this is symmetric, non-degenerate covariant tensor, which is of rank 2. And usually, I mean, for purposes of physics, it is of Lorentzian signature. So it is defined on a 4-dimensional manifold M. I call M manifolds here. So what it really reduces to is Riemannian geometry of such manifolds defined for a connection gamma, but in fact pseudo-Riemannian because of this Lorentzian signature. So the connection in this case is symmetric, which means the torsion tensor vanishes, and it is metric, which means that covariant derivative with respect to this connection of the metric is 0. And connection, because of these limitations, becomes fully expressed in terms of the metric and its derivatives, first derivatives actually. So the connection is not an independent object, and this is what was criticized by Cartan, who liked to think about connection and metric as completely separate objects, maybe not related at all. And so we have to stick to this general philosophy and think about the theory which has metric and connection as totally different fields, and then try to think about topological quantum field theory in terms of such of the connection actually, because metric is something which will be forbidden at certain moment. So let us talk for a short while about topological quantum field theories with and without metric. So topological quantum field theories are such mathematical constructs actually, but which concern manifolds, which formally resemble quantum field theories known from theoretical physics. And as Professor Witten's approach showed, usually it is formulated in terms of path integrals, which are actually not well-defined objects. And these measures, somebody was asking yesterday, these measures which are there are normally not well-defined, but there are some rules of manipulations of these objects. So physicists can do a lot of interesting things and even do some mathematics with them, apparently. So what we want from such quantum field theory is that it is built only using smooth structure of the manifold, and this way we hope for getting topological invariance of the manifold. So they should be independent of the extra geometric structures like, say, metric. This is what Witten actually assumed. So, but there might be still metric present, but then we have to do a path integral which integrates over all these different metrics, which we can define on the manifold. And it's even not clear how to treat these different signatures, etc. But formally, this is like that. So these are topological quantum field theories with metric. So the other topological quantum field theories which are built without metric use connections on principal bundles or in terms of physics gauge fields, such as known from particle physics. And we know Maxwell fields and Young-Mills fields, which are U1 and SU2 such gauge fields. But normally they require a metric to build a Lagrangian describing these fields. So then they are explicitly dependent on the metric. So yeah, I maybe, yeah, so we have a connection then which is smooth, consists of Lie algebraic part and differential, I mean, one form. So locally it looks like that. I will quickly go through that, especially that Hannah will probably do a little more on that. So, but normally we don't have this, as I said, independent from metric, but in 3 dimensions, this is this miracle of Chern-Simons Lagrangian, which looks like that. So we have, and it is of 3rd order, so despite we can define the action and topological invariant will have this form. The problem is that it is non-Gaussian, and this is not so easy to analyze, but of course, physicists, especially Professor Witten, found a way to do it in special cases, then as we've heard, also extend to other, because of the gauge invariance, we have to have a specific h bar constant, which we usually know from physics, but this h bar is 4 pi over k. K is integer. And when we add homolomies, we get, of course, the whole thing as such path integral. And in case when the manifold is S3, this is more or less John's polynomial, which of course is close relative of Kaufman bracket. I should remind about Professor Kaufman's contribution here. And of course, there are many others. So we would like to combine Cartan's philosophy, and I should first talk about this Cartan's philosophy with topological quantum field theory philosophy. So Cartan's philosophy on geometry is that metric and connection are independent geometric fields on a manifold, and connection is characterized by curvature and torsion. So this, because connection itself is not a tensor field, one should remember that. So this creates certain problems, but curvature and torsion of connection are, and the interaction between these two fields is via non-metricity, which means covariant derivative with respect to gamma of the field G. So it is another tensor field which could be in play. And quickly, definitions of those, but the classification of geometries accordingly to Cartan, or application of his general philosophy, is that Riemann geometry is when curvature, so defined, is not equal to 0 in general, and torsion and non-metricity is 0. As I talked about, connection in such case is fully dependent on metric and is called Levi-Civita connection, but it not necessarily should be this way. The Weizenbeck geometry is such that curvature is 0 actually, but in this case, torsion of the connection is non-zero, but still the connection is metric. There is also Weil geometry when non-metricity is non-zero and all others are, interestingly enough, 0. So this is another kind of geometry. And Riemann-Cartan is such geometry that both curvature and torsion are non-zero, but still metricity holds. And the physicists are, of course, eager to study everything, and so metric affine theorists put everything to be non-zero in general. So if we merge Cartan's philosophy with topological quantum field theory without metric, then we lose non-metricity from the view at all, because there is no metric, so we cannot calculate non-metricity for something which doesn't exist. So we have some Riemann-like geometry with curvature non-zero and torsion equal to 0, Weizenbeck-like geometry where Riemann tensor is 0, but torsion is non-zero, and Riemann-Cartan-like where both of them are in general not 0. And these two first of these theories were studied before, in no connection to topological quantum field theory or any manifold invariance, by Kijowski, who studied Riemann-like geometry with curvature non-zero and torsion 0, but
it was affine theory, which means there is no metric at the beginning, but only connection. And Sławianowski studied Weissenbeck-like geometry, where curvature is zero and torsion is non-zero. And the remaining one wasn't studied, but we can imagine how it looks. I mean, it's quite different, probably combination of those two. I will talk about it at the very end, more or less. So in order to define classical field theory from which we can build this quantum field theory from which we might construct some topological invariants, we need Lagrangians on the manifold, and these Lagrangians are scalar densities. And they integrated over the manifold give the action of the classical field theory. So why scalar densities and what are they? So we do integration for calculating action of the volume of the manifold, so over dx1 to dxn, but this should be invariant under the change of coordinates. And observe that if we take y coordinates, dy1 to dyn, will produce the Jacobian of this transition multiplied by previous volume. So it is not invariant. Such volume form would not be invariant under change of coordinates. But if we have a metric, so which, so then its determinant actually produces inverse of Jacobian squared in transition to the different coordinates. And therefore, square root of such determinant produces what we need, inverse of the Jacobian, maybe up to sine. So we have to limit ourselves to orientable manifolds, but this is not probably very big limitations. And then the proper volume scalar density is square root of determinant G times this dx1 to dxn, because in every other coordinates, it will look just the same. So the general form of a Lagrangian would be that we have to build a scalar from whatever fields we have times this volume form. So if we have no metric, we are really quite limited in the choice of this volume form, as well as building scalars from whatever fields we have. But imagine that we have some covariant, second rank covariant tensor, say symmetric, then we can build something like volume form. So in this quotation mark, and try to go along the lines which I showed. And this is what Kijowski and Sławianowski did. And I will describe in some detail now. So original Kijowski model deals with matter fields, but I will ignore them because we are interested now in only manifolds, but it makes also sense in the absence of matter. So this is some small technicality I don't want to talk about. Yeah, so we construct a theory of one field connection, which has these three indices, alpha, beta, gamma, and it has to have torsion equal to zero. This is what Kijowski assumed, that this torsion disappears. We remember that this is Riemann-like assumption in Cartan's classification. So we do it by adding to Lagrange multiplier lambda, where these lambdas are tensor densities of 2-1 type. So when we have a connection, we can have two tensors, torsion, which already is 0, and curvature, which is a tensor of type 1, 3. And we need a tensor of type 0, 2. But we know that there is a very well-known Ricci tensor, which doesn't require any metric to construct because we just take this trace of the Riemann tensor and we get Ricci tensor without any manipulation requiring metric. The Ricci tensor in general is not symmetric. So in order to have symmetric, we just do symmetrization. So we end up with something we needed. We have a symmetric tensor and we can build the Lagrangian. So it will be a square root of the determinant. I put it in absolute value because we don't know the sign. So square root of determinant of this symmetrized Ricci tensor. And we can add some scalar function of the connection gamma here in general. But if we don't have a metric, we cannot build anything reasonable besides some numerical factor, some scalar, some number. So the Lagrangian finally has this form, some scalar factor times square root of determinant of k mu nu plus this constraint that S is equal to 0. And I have to add this digression that despite there is no metric, Kijowski managed to introduce it in some nice way. Using multisymplectic approach to classical field theory, he introduced conjugate momenta of the field gamma, which are variational derivatives of L with respect to k mu nu. And the momenta are tensor densities of type 2, 0. And this allows to introduce a tensor, actual tensor of 2, 0 type, which we call, not surprisingly, G mu nu, but this is like inverse of the standard metric. But in case it is invertible, we can define also the G mu nu with lower indices and square root of the determinant of it. And when we perform a Legendre transform, this is accordingly to what usually is done in physics. We go from, say, speeds to momenta. We define a Hamiltonian for the field by this formula and rewrite in new variables phi mu nu or k, G mu nu, and we get this as Hamiltonian of the theory, where G mu nu, the most important part is probably this G mu nu, K mu nu, because it can be still rewritten because G mu nu is symmetric. So we can come back to the full Ricci tensor because asymmetric part would disappear during, when taking this G mu nu, R mu nu. So this is a Hamiltonian which looks exactly like Lagrangian of the Einstein field theory in the vacuum with a cosmological constant. This is the price that we have non-zero cosmological constant. And of course, there are these constraints which are following, but so this is, I end this digression and come back to to different approach by Sławianowski this time, but it will be an affine formulation of it because he originally did it in frame and coframe fields, but I wanted to go along this Cartan philosophy. So, but what he did actually, he defined a connection which has 0 curvature, but non-zero torsion. So it is Weizenbeck-like geometry. We have no metric, so we have, again, we have no choice but find a tensor of second rank, which will be built this time from distortion tensor of the connection. And Sławianowski actually showed that this is the only choice of such symmetric second rank tensor is by taking such traces or combinations of those of those torsion fields. So it is square second order polynomial in S. And the Lagrangian, because of that, will have this part square root of determinant gamma mu nu, perhaps with absolute value just in case, and the constraint that curvature disappears, where these lambdas are for some Lagrange multipliers. Again, these are tensor densities because the Lagrangian is a scalar density. So when we have the classical field theories, which I briefly described above, we can go and define appropriate path integrals. For the Kijowski theory, it will be looking like that, obviously. So some path integral over all gammas, all possible connections on the manifold. And here is an integral over the manifold of this Lagrangian, which I try to construct. And in Sławianowski theory, it's, of course, similar, very similar structure of the path integral. And observe that in both cases, the Lagrangian has the square root form, which from the point of view of physicists is something horrible. And this was for quite some time stopping Hannah and I from doing things. And but recently she found a way slightly breaking this general covariance, which means diffeomorphism invariance of the theory, and we hope it's still justified, and getting rid of square root. She will talk about it in the next talk. And interesting new option opens that if we take Riemann-Cartan-like geometry, which nobody touched upon before, we can just combine those k mu nu and gamma mu nu with some coefficient. I called it d, doesn't matter, and consider such path integral. Of course, it will be again the same issue with square root of some complicated polynomial which contains also derivatives, etc. And it is high order polynomials. And the order, of course, grows with the dimension of the manifold. So this is really difficult to analyze. And so I said that this is irrational function as a Lagrangian. So it is a difficult thing, but hopefully there will be some continuation. And in three-dimensional case, it looks, I mean, I'm not sure exactly, we didn't study this in detail. Maybe there are some issues, but we can define so this looks like the formulas disappeared, but we can define a la Chern-Simons in 3 dimensions. We can add this holonomies just as for Witten approach, Chern-Simons theory. We can try this, and of course, try also to compare. Does this produce some not invariants, in particular for 3-dimensional sphere, or not? And so there is still very open field to research. of course, we have to, I mean, we focused, as I said, on this square root issue. So we didn't study much outside of that or in particular dimensions, but Hannah will talk a bit about some other things, development in Sławianowski theory, but I think I will finish here. So thank you for your attention and live long and prosper, Lou. We love you, so hope for long, prosperous life.
Great.
Thank you.
Thank you very, very much for that talk. That was very interesting. Thank you. I am going to stop the recording.